Okay, let's begin our fourth session here, chapter 4 of this booklet, linear first order ODEs and Bernoulli equations. Okay, so let's begin with section 4.1 on integrating factors, but you need to know what a first order linear ODE is. So that's an equation of the form here of equation 5, y dash plus a function of x called p times y is equal to q of x, where y dash is equal to dy on dx. Now, of course, you could have a linear equation that's a function of t. You just have to replace all of the x's with t's and then proceed. Okay, so our task here is to learn how to solve first order linear ODEs, and then to consider a number of examples, applied examples. Okay, so we need to multiply by what's called an integrating factor, so that in multiplying by that integrating factor, we make the left-hand side of this equation into something separable. All right, so what is the integrating factor? Let's set out I for integrating factor. I of x is equal to e to the power of the integral of p of x dx, where the p of x is the coefficient of the y when you put it in this form. So multiplying equation 5 by I of x gives us, so let's look at the right-hand side first. I of x times q of x is equal to I of x times y dash plus p of x times I of x times y, so just as we have there. Now, what is I? Well, we can notice that we set out I to be equal to e to the power of the integral of p of x dx, so that's just a substitution of the value of I there. And now, notice that the derivative of e to the power of the integral of p of x dx requires the chain rule of integration. So when we set out the chain rule of integration, now let me just do that here on the right hand side of my screen. So we've got e to the power of, hang on, e to the power of the integral of p of x, and then with respect to x. Okay, so let's set this out with the chain rule here. Now this up here would be our letter u. Okay, so I'll copy that. I'll put this in brackets. And then we want to set that out here as well. So it looks like they would cancel if they were fractions, right? Innate to memory of the rule. Remember, they're not fractions. Okay, so this is what the chain rule tells us. Now, what we have here on the left of the right-hand side of this equation is the derivative of e to the u with respect to u, which is just e to the u. So we can include a simplification there and say that that part is just e to the u, which is e to the integral of px dx. And then on the right hand side of this expression here, we have the derivative of the integral, so that's just p of x. So we can replace that there with p of x. So we see then that this derivative of that integral is p of x times the integral, sorry, p of x times e to the integral of p of x dx. Okay, so that this actually gives us p of x e to the integral of p of x there. So we can replace p of x times e to the integral of p of x dx with the derivative of e to the integral of p of x dx. Okay, and now at this point we can call this I dash, right, because that's the derivative of I. And so we have I times y dash plus I dash times y, which by the product rule of differentiation is the derivative of the product of y with I. Okay, so this allows us to separate the ODE now, because what we have is d on dx of iy is equal to I times q of x. Because remember, we multiplied that right-hand side of this equation also by I. Okay, and now it's separable, so what do? We separate it. So let's put the dx on the right-hand side. And notice that I is a function of x. So on the right here, we have just functions of x. On the left here, we have diy. Okay, so now at this point, we include the integration symbol. So we have the integral of 1 with respect to iy. And then on the right-hand side, we have the integral of something with respect to x, and that something is I of x times q of x. All right, now on the left, that integral is simple because we have just the integral of 1 with respect to iy. So that just becomes iy. And then on the right, we have an integral to do. Presumably, we can do that integral. Okay, and then finally, what remains is to divide both sides of this new equation by this integrating factor I. And so when we do that, we will obtain y as a function of x is equal to 1 over I, or I to the power of minus 1. Okay, which gives us now our equation 7 that we have at the bottom. So we see that the difficulty in actually doing this, if we just use equation 7 once we recognize that the equation is linear and what our integrating factor is. So the difficulty is in calculating the integrating factor first and then calculating the integral that we have on the far right here. Right, so that's the difficulty in performing a solving of a linear first order ODE. Okay, so next I think we're going to look at some examples. Let's scroll on to the next page. So we have our first example here. Solve the first order linear ODE. Y dash is equal to 2xy plus x using an integrating factor. So this equation is also separable, so there's another way to do it, right? Which is comforting to know that if you can't do it one way, then maybe you can do it another way. So some equations can be both separable and linear, which gives you two ways of doing it, at least. Okay, so to do this one, using the techniques of linear equations, we first want to rearrange it so that we have all the y's on the left and a function of x on the right-hand side. So here we take the 2xy over to the left-hand side next to the y dash. And then we've got to recognize our p of x and our q of x. So here we see that p of x is minus 2x and q of x is just x. So now we need to integrate p of x, which is to integrate minus 2x with respect to x, and we get minus x squared. And you can obviously just check by differentiating minus x squared. When you do so, the 2 comes down and you have minus 2x. Okay, now our integrating factor is e to the power of that, or e to the minus x squared, so we let that be I. Okay, next we could just use this equation 7 directly. Or you could go and follow the procedure that we did on the previous page. You could follow that again if you want. Or you can just use 7 directly. Okay, so in this case, we'll just use equation 7 directly. So 1 over I, or e to the power of minus I, is just e to the power of plus x squared. So that's what we will have in front of our integral. And now next to that, we've got to integrate the integrating factor times q of x. So in this case, it's x for q of x. So we have x e to the minus x squared that we have to integrate. All right, now with this one, we can do this integral by substitution, because you can notice that the derivative of minus x squared is minus 2x. So these are very similar, right? The derivative of minus x squared is very similar to just x. So we can compensate for that by putting in a minus 1/2 in front of the integral, and then include the multiplicative inverse inside the integral, so we can view this as a derivative using substitution, which we learned in the last lesson. Okay, so that makes the integral of minus 2x e to the power of minus x squared equal to just e to the minus x squared, and then plus our constant of integration. Okay, so we get now that y of x is minus 1/2 e to the x squared times e to the minus x squared plus our constant of integration. So our last step here is to expand, if you want to. So what happens when you expand this? You get minus 1/2 e to the x squared minus x squared in the exponent of e. And so that gives us an exponent of 0. So we have e to the 0 there. And so we just have minus 1/2, right? But when we multiply minus 1/2 e to the x squared times c, we have minus 1/2 times c and then times e to the x squared. So we can just declare a new constant a at that point to keep this tidy. And so we have our general solution. Y of x is equal to minus 1/2 plus a e to the x squared. All right, so that's a fairly simple example. So let's move on and look at another equation. So let's solve the initial value problem. Y dash is equal to x squared plus y, with y of 0 equal to 0. So this one has another step. We've got an initial condition which gives us a particular solution to the ODE, right? In other words, we are able to solve the initial value problem there with that initial value. So we see that this equation is linear because we can take that y over to the left-hand side and put y dash minus y is equal to a function of x, in this case x squared. So p of x is just minus 1 and q of x is x squared. We need to calculate the integrating factor first. So that's e to the integral of minus 1 with respect to x, which is just e to the minus x. And then use equation 7, which is what's highlighted there on the right-hand side. Or just repeat the entire procedure again if you like. Okay, so our integrating factor here gets multiplied in. We know what that is. So the inverse of that is e to the x. So we have e to the x integral of x squared e to the minus x dx. Now we did this integral in our previous video, right? And that was an integration by parts that we had to apply a couple of times. And so we got minus e to the minus x outside of x squared plus 2x plus 2, and then plus our integrating constant of integration c. Okay, so now we need to expand in e to the x, which was our multiplicative inverse of the integrating factor I. Okay, so we multiply that in there, and we can see that that will allow us to cancel the e to the minus x, right? Because we add the exponents, e to the x multiplied by e to the minus x gives us e to the 0, And so this just makes a factor of -1 out this front of this quadratic polynomial. So we can multiply that -1 in now and get -x squared minus 2x minus 2. And then when we multiply in e to the x times our constant of integration, we have c e to the x. Okay, so that gives us our general solution there, but now we need to solve the initial value problem and use our y of 0 as 0. So our next step is to sub in x is equal to 0 and y is equal to 0. So we do that. Now, subbing in 0 for x there gives us 0. We have 0 here. We have -2 here. And then over here we have c times e to the 0, which is just c. So on the right, we're going to have c minus 2. On the left, we have 0. And so that just gives us that c is equal to 2. And so we have our particular solution to the equation. Y of x is equal to -x squared minus 2x minus 2 plus 2 e to the x. Okay, so next we move on to an applied example. So let's have a look at this circuit. Now the drawing is not the best. It looks like it's doubled a little bit in some places, but I think it's clear enough to see. Okay, so we've got a circuit. It has a battery, it has a switch, it has a resistor, and it has an inductor, which evens out the charge in the circuit. So this is what the circuit diagram would look like here on the right of that diagram. All right, so this is an example from physics, or engineering if you like. So consider the diagram. So what we're going to do here is model the current over time as the switch is turned on. We let J of t denote the current in amps, let R denote the resistance in ohms, let V1 denote the voltage drop across the resistor, let V2 denote the voltage drop due to the inductor, and let L denote the inductance in henries. Let E of t denote the supplied voltage due to the battery. Okay, now using some laws of physics, we have the equation V equals IR, but in our case, we've used the letter J because we want to use the letter I later for our integrating factor because we're going to find a linear equation. So in other words, V equals IR, it can be expressed here as V1 equals JR. And also we have V2 is equal to L times J dash of T. All right, so those laws come from physics. Kirchhoff's law tells us that E of T is the sum of the voltage drops. And it follows that we can substitute to obtain the differential equation. E of T is equal to JR plus LJ dash. So we're just taking the V1 and the V2 and we're subbing in these two. JR goes in there and LJ dash goes in where the V2 is. And we obtain a differential equation. Okay, now is this a linear equation? Well, it would seem to be in the letter J, right? Because we can divide throughout by L. Let's have a look here at the next page, or the next equation first. We can rearrange that equation to obtain J dash plus R divided by L times J is equal to 1 over L times E of T. So we've divided that previous equation by L and swap sides. So now we can recognize this equation as linear. The P, which is now a function of T. So P of T is R over L, and Q of T is 1 over L times E of T. All right, so let's suppose we have some values now for these constants. So the initial current is 0 amps. The battery supplies a constant voltage of 60 volts. The resistance is 12 ohms and the inductance is 4 henries. So that gives us a particular equation here, having subbed in those values. So let's have a look. We had R over L. So in this case, R over L is 60 divided by 12. Is that right? No, so the inductance is 4. So 60. Yeah, 12 over 4 is 3. Okay, and then the right-hand side we get 15. Okay, so initially we had 0 amps, so we've got the initial value problem. J of 0 is 0. So clearly we've got a stable equilibrium at J equals 5 amps. So we see already that the current will approach 5 amps as t goes to infinite. So this equation is linear with P of t is equal to 3 and Q of t is equal to 15. So first we want the integrating factor. I is equal to e to the power of the integral of 3. So the integral of 3 is easy, it's just 3t. So our integrating factor is e to the power of 3t. Now remember, we multiply by that integrating factor and then use equation 7, right? And so that gives us then that this is 15 e to the minus 3t times the integral of e to the 3t dt. So this integral is easy. We just have 1/3 e to the 3t and then plus our constant of integration. So that's why we have a 15 there becoming 5 in the next line, because we've divided by 3 when we integrated that. So we have 5 e to the minus 3t, that, you know, what we have in equation 7 there, and then times that integral once we've pulled out the 1/3. Okay, so now simplifying this, we multiply the e to the minus 3t in, and we have 5 plus a new constant a times e to the minus 3t. So this is our current as t goes on. Right now, as t goes to infinite, now you could just take a limit as t goes to infinite in this expression here, and you can see that the current will approach 5, just as we expect there when we look at equilibrium solutions, right? Without having first solved it. So that makes sense and agrees with what we got. Okay, now if we use our initial value j of 0 is 0, we sub in t as 0, and on the right hand side here we have 5 plus a, and then on the left we would get 0. So that gives us that a is minus 5, and so we get j of t is 5 minus 5 e to the minus 3t. All right, so let's have a look now at another example from physics. Suppose we're going to model the velocity of a skydiver falling from a plane, taking air resistance into consideration. So we would expect then that the terminal velocity would be in play. Okay, so we're going to give an expression for terminal velocity. So this comes from the citation number 3 there in the references, and page 12 and page 44 of that book. So just have a look at this. Now we're on page 38 of this workbook now, but let's have a look at what the third book is. Okay, so that's Virginia W. Nunberg, Ordinary Differential Equations from Calculus to Dynamical Systems. So that has a little discussion on this problem. So let's go back now to page 38. Here we go. Okay, so Newton's second law of motion states that the resulting force is given by F equals ma, where m is the mass of the skydiver, a is the rate at which the velocity changes, or the acceleration of the skydiver. The force acting on the skydiver due to gravity is mass times gravity. Let's assume that g is 9.8 meters per second squared, and the force due to air resistance is proportional to the velocity of the skydiver to the power of a constant. So in other words, k times v to the power of c, where k is the coefficient of friction due to air resistance. Now this force acts in the opposite direction of gravity, so we're going to get mass times acceleration, or m times v dash, is equal to mass times gravity minus that air resistance force, which is in our case minus k times v to the power of c, because it acts in the opposite direction of gravity, right? It's a resistance force. All right, so we have a differential equation. Now, if c is equal to 1, then we have a linear ODE, because we can just sub in c is equal to 1 there and get v dash plus k over m times v is equal to g once we divide throughout by m. Right, so that's linear, but in other situations, like perhaps through other fluids other than just plain air, maybe you might want to be able to do this on a surface such as Mars as well. So in that case, you may have different constants. So you may, in that case, have a nonlinear equation to solve. Okay, so we can see that there's a stable equilibrium solution when v to the power of c is equal to mg over k, which we can interpret as the terminal velocity of the skydiver. So dividing or raising to the power of 1 on c will give us that v, the terminal velocity, is the cth root of mg over k. Again, if c is equal to 1, we have a linear ODE, so let's go ahead and solve it. In that case, the integrating factor will be e to the power of kt over m. And so equation 7 from before, which is just this here, gives us that v of t is I to the power of minus 1 times the integral of I times q of t. Now q of t in our case is just g, which is constant. We worked out that the integrating factor here is e to the power of kt over m. Okay, so that's right here. And so we've got to integrate g times e to the kt over m. Right, but that's a very easy integral. It's just mg over k. So in other words, the inverse of that constant, k over m, is just m over k. And so multiplied by the g that was already there. Okay, then plus a constant of integration. Let's call it a here. Now, we want to simplify this expression, multiply in by e to the power of minus kt over m. And so what happens is e to the power of minus kt over m plus kt over m gives e to the power of 0, which is 1. And so we just have mg over k there. Now multiplying in the e to the power of minus kt over m times a just gives us a times e to the minus kt over m. Okay, so we have our general solution in the case that c is equal to 1. Right, using techniques of linear ODEs via integrating factors. And we can see here, as we take the limit as t goes to infinite of the right-hand side of this equation, a to the e to the power of this minus kt over m, because that's negative there, assuming k and m are positive, that part of it will tend to 0 as t goes to infinite, and we just have remaining mg over k, right? So which agrees with our terminal velocity there, right? In the case that c is 1. Now, if c is not equal to 1, suppose, like, for example, c is equal to 2, then we have a nonlinear ODE to solve in that case. And so we would take the separable approach because it's a separable equation. Okay, so let's look at this. If c is equal to 2, then we have dv on dt is equal to g minus k over m times v squared, which is a nonlinear equation. And so since it's separable, we can still solve that fairly easily. So separating the equation gives dv over alpha minus v squared, where here we set out, let alpha be equal to mg over k, right, just to make this look simpler. Okay, and on the right-hand side, we have the integral of k over m dt, which is easy to integrate. We just have k over m t plus a constant of integration. Okay, now we want to simplify the left-hand side here using some techniques that we learned in the last session together. Substitution, okay, the integral of dv over alpha minus v squared, well, we can pull out a 1 on root alpha there because we want to introduce that up here in the d part of it, right? So we want to integrate this by substitution. Now you would introduce this 1 on root alpha there and include a derivative so that you can check out if this is actually accurate. Okay, so we can write this as the integral of dv over root alpha over 1 minus v over root alpha all squared. Okay, I feel like I should probably demonstrate exactly how this works here at this point. So let's just write in this integral. I'll put in a fraction. Well, I've got 1 over 1 minus, in brackets, the fraction v over square root of alpha all squared. Okay, and then we said with respect to the variable v over the square root of alpha. Okay, so let's just narrow in on, focus on this particular integral here to verify that it is indeed what we have there on the left. Okay, so I will introduce a dv here, which is just substitution. Okay, and now I have a derivative to evaluate, right? So this is saying what is the derivative of v over square root of alpha with respect to v. Okay, so doing that derivative there will give us 1 over root alpha because that's a constant there. Right, so 1 over root alpha there because that's the derivative of v over root alpha with respect to v. Okay, so now I've completed that substitution there in reverse. Okay, so now I have 1 over root alpha. This is a constant, but I can multiply this in on the left part of this. So that would give us, let's go and put in a new line here. So that gives us root alpha there and root alpha there. Okay, so we have this now. Now let's square this term. So when we square v over root alpha, we have v squared and then we have root alpha squared, which is just alpha. Okay, so we have this so far. And now what we want to do is simplify the product of root alpha divided by, or the product of root alpha and 1 over alpha, which gives us 1 over root alpha. When we simplify that. Okay, now we want to simplify this a little bit more, because at this point we were looking at all of this times 1 over root alpha, right? So far we've established, so we have shown that this, you know, which is what we had here, we had it displayed like this, okay? So we've shown that this is equal to this one, okay? But you notice here that what we have in the middle here is 1 over root alpha times this on the left. So let's go ahead and multiply throughout by 1 on root alpha. Okay, and then simplify the result here on the right hand side. So we can take that 1 on root alpha inside. So let's do that, which puts this here in the denominator. Okay, so we have this so far. All right, now I can multiply that root alpha in, which is what we want to do next. So we've got root alpha times root alpha, and then we've got root alpha over root alpha there, right? And so root alpha times root alpha is root alpha squared, which is just alpha. And then over there on the right, we can see the root alphas canceling. All right, so we then have root alpha there. We have the cancellation of the root alphas. And so we've now verified what we had there at the bottom, right? So that's a fair bit of working to go from there to there. But we've now verified that those are the same thing. Okay, so we can proceed now to finish this off. Now let's recognize v over root alpha as the letter u, so that we have du over 1 minus u squared. Okay, so carrying on. Now we did this integral, we did so via a hyperbolic substitution, remember in the last session. So let's have a look at what we did with that. So we've let u equal v over root alpha. Now we, to complete this, remember what we did is we said let u equal tanh of theta, which is sine over cosh. Okay, so remember the identity, cosh squared minus sine squared is equal to 1, which makes this hyperbolic because x squared minus y squared equals 1 is a hyperbola. And actually, why don't I just display that hyperbola here? So I'll just write contour plot. X squared minus y squared equals 1. Let's give a plot range. And so you can see there's a hyperbola there, right? So that's why we call this a hyperbolic functions. All right, anyway, so we set out u is equal to tanh, but we've already done this in the previous session, I believe. We've already done this, so we can just gloss over the details here. We found that this integral is arctangent of u, which is v over root alpha. Okay, so that gives us the solution there to our integral, which was the difficulty in this part of the problem. But we obtain arctangent of v over root alpha is equal to k over mt plus our constant of integration. Remember, this was the easiest side of that integral. So next, now that we've got this relationship, we want to take the inverse function of tanh, the inverse function of arctangent, which is just tanh. And so that would give us v over root alpha is equal to tanh of k over mt plus a. Okay, now there's a rearrangement of that because of the identity of cosh and sine, right? Which allows us to simplify this in simpler terms, just as powers of e, right? So this becomes the square root of mg over k times 1 minus e to the minus 2 k over mt plus a, and then over 1 plus e to the minus 2 outside of k over mt plus a. Okay, now clearly as t goes to infinite, this part of it goes to let's see, what does it go to? We've got a minus power there, so that goes to e to the 0. And we get v of t approaching the square root of mg over k, which is our terminal velocity in that case. Because if we go back to that equilibrium solution in equation 9 with c equal to 2, let's go and have a look. Remember, equation 9 says terminal velocity is supposed to be mg over k to the power of 1 over c. Now with the c equals 2 case, we've just got a half, which would say that this is the square root of mg over k. Okay, so that's in agreement with what we had there by looking at equilibrium solutions. And you can see by this integral or solving this ODE by the separable approach was quite involved, right? It was a difficult integral to do. But we knew before solving that our terminal velocity would be the square root of mg over k, without having to go through all the difficult details of that integral. Okay, so I think we have one more example here, which comes from, say, chemistry, because chemistry's got a lot of mixing problems. All right, suppose here we've got an aquarium. Now it's just water here, right? So, but there's salt involved. So let's call this a chemistry problem. But I have had a marine aquarium in the past, and I know well what it's like to mix salt and so on. So I didn't do all these calculations at that time, though. An aquarium initially contains 150 liters of water with 20 grams of salt dissolved in it. In order to accommodate a new fish, the concentration of salt must be increased from 20 grams per 150 liters to 1 gram per liter. This new concentration is to be achieved by releasing water into the tank with a salt concentration of 3 grams per liter at a rate of 2 liters per minute. At the same time, mixed water runs out of the tank at a rate of 2 liters per minute. Our task is to model the amount of salt, x of t, at time t in minutes. All right, so the rate at which the salt concentration is changing with respect to time is x dash of t, and this is just the rate of salt in minus the rate of salt out. So we've got an inflow and an outflow. Okay, so substituting in values, we've got 2 liters per minute times 3 grams per 1 liter, which is here. So that's our rate in, and then our rate out is 2 liters per minute times x of t times, or g over L, right, per volume. Okay, so subbing those values in and simplifying, so 2 times 3 is 6. So we have x of t is equal to 6 minus 1 over 75 x of t. So that's a linear equation, and we can write this as x dash of t plus 1 over 75 x of t is equal to 6. And I can see my spacing in the document's a bit off, so I'll have to fix that later. And we've got an initial value of x of 0 is 20. Okay, so we want to solve this using an integrating factor. Now our p of t is 1 over 75. So the integral of 1 over 75 is 1 over 75t. That means then that our integrating factor is e to the power of 1 over 75t. And q of t is the right-hand side, which is just 6. Okay, so equation 7 gives us, which was just what we have here. Equation 7 gives us e to the minus 1 integral of, I to the minus 1 e times the integral of I times q of t with respect to t. Okay, so subbing that value in, we've got e to the power of minus 1 over 75t times the integral of 6 e to the 1 over 75t with respect to t. Now that integral is fairly easy. So we have 75. Let's see, the integral of 6 e to the 1 on 75t. Okay, so 6 times 75 e to the 1 on 75t, and then plus our integrating factor. So that's times there, not 6 point. All right, so multiplying those together and then multiplying e to the minus 1 on 75 in, the product of 6 and 75 is 450, so we've got 450 plus c times e to the minus 1 on 75t once we multiply that in and expand. All right, so this gives us a way to model this. We've got the general solution, but we need to take into consideration the initial salt concentration there. 20 grams of salt initially. So x of 0 is 20. So we sub in t is 0, and we have e to the power of 0 is 1 for this part. On the left-hand side, we have 20. Okay, so that gives us that c is 20 minus 450, which is minus 430. So we have x of t is 450 minus 430, e to the power of minus 1 over 75t. So that's our particular solution that allows us to model the concentration of salt. So the question now is, when is the salt concentration what we wanted it to be, which was 1 gram per liter. Okay, so we want to solve the equation for when is x of t equal to 1 gram per liter. So then we have 1 over 150, 450 minus 430 e to the power of minus 1 over 75t is equal to 1. Now 150 is our volume there. Okay, so rearranging that equation gives us, so we would multiply throughout by 150, we would take the 450 over, giving us minus 300, and then we would divide that by minus 430 and obtain 300 over 430 is equal to e to the power of minus 1 over 75 times t. Okay, next we want to take natural logarithms of both sides and obtain minus 1 over 75t is equal to the natural logarithm of 300 over 430, which we can simplify as the natural logarithm of 30 over 43, and then multiply both sides by minus 75 to give us t, the amount of time that we need to wait. So t is minus 75 natural logarithm of 30 over 43, and then we just calculate this in the computer or the calculator, and we get approximately 27 minutes that we need to wait. Okay, so let's now move on to Bernoulli equations. What is a Bernoulli equation? Well, it's an equation that looks almost linear. Well, it looks linear on the left, but not so on the right-hand side. No fear, however, because we can turn this into a linear equation. Okay, but notice first that when n is equal to 0, we actually have a linear equation. When n is equal to 1, we can rearrange this to make it linear easily. Okay, so let's in general assume that our Bernoulli equations have n equal to a number greater than 1. So when n is not equal to 1, we make the substitution z is equal to y to the power of 1 minus n. And that makes the result linear. because we can just use the chain rule here of differentiation. So z dash or dz on dx is dz on dy times dy on dx by the chain rule of differentiation. And so when we set out the substitution, z is equal to y to the power of 1 minus n, the derivative of that, being dz on dy, is 1 minus n times y to the power of minus n, and then we can express dy on dx as y dash. Okay, so we're going to use this to simplify equation 10 there to show that it's a linear equation. So by substitution, let's see, what have we got here? Y dash. Okay, so we can just rearrange y dash here, dividing by 1 minus n times y to the minus n, and so that would be 1 over 1 minus n times y to the plus n. Okay, and then sub into equation 10 there. So that's what we do here. We have z dash times 1 over 1 minus n times y to the positive n plus n plus p of x times y of x is equal to q of x times y to the power of n. Okay, so multiplication by 1 minus n times y to the power minus n gives us an equation that's linear. So we have z dash plus 1 minus n times p of x times z of x is equal to 1 minus n times q of x. So it's linear. Now we see that it's linear with a new a new p of x, so you might want to call it uppercase p of x, equal to 1 minus n times lowercase p of x. All right, so let's have a look at an example here. It looks fairly simple. Find the general solution to the ODE y dash plus x times y equal to x y squared. This is a Bernoulli equation with n equal to 2. We've got p of x is x, which is also q of x. We let z be equal to y to the power of 1 minus n, but with n equal to 2, 1 minus n is minus 1. So z is y to the power of minus 1, or 1 over y. And the equation, I guess it would be equation 11 above. It must be named the same in my document there. Becomes z dash minus, now remember 1 minus 2 is minus 1, so that's why we have a minus there. So z dash minus x times z is equal to minus x. So that's fairly simple, a fairly simple linear ODE to solve. We multiply by the integrating factor e to the integral of minus x dx, which is e to the minus a half x squared. And then we get, again using equation 11 for linear equations, or sorry, equation 7 for linear equations, z is equal to e to the 1/2 x squared times the integral of the integrating factor there times q, which is minus x. Okay, so we've got to integrate minus x e to the minus a half x squared. Now that happens by a simple substitution, because the derivative of minus a half x squared is just minus x, right? So that's in front. So this integral is fairly easy. We just have e to the minus a half x squared there, and then plus our constant of integration. Okay, so finally we want to multiply in e to the 1/2 x squared. It makes the product of these two be equal to 1, and then we have plus c times e to the 1/2 x squared. Okay, so this gives us the value of z, or the function z. But remember, we set out that z was 1 over y. Okay, that makes y equal to 1 over z, so we could just take the multiplicative multiplicative inverse of both sides there to get y. So y of x is 1 over 1 plus c times e to the 1/2 x squared is our general solution to this Bernoulli ODE here. Okay, so that wasn't our last example. Let's see. I think this one is our last example for today. All right, so recall the logistic equation, which was equation 1 for population growth, given in example 2.3. Now, we solved that one by the technique of separable equations, but this time we can use the fact that we have a Bernoulli equation. So we have dp on dt is kp outside of 1 minus p over a. Okay, so if we expand this and rearrange, then we have the Bernoulli equation, dp on dt minus k times p is equal to minus k over a times p squared. That's a Bernoulli equation with n equal to 2. So very similar here. So we have the form of equation 11 with n equal to 2. Okay, so we set out our p of t, our q of t, and then we just have a linear equation with z equal to p to the minus 1. So we take an integrating factor here, which is e to the kt, and multiply that by that, and then we use equation 7 again, which is what I've got highlighted on the right. So e to the minus kt times the integral of k over a, e to the kt dt. That integral is easy. And we have e to the minus kt times, in brackets, 1 over a, e to the kt, and then plus c. Okay, so finally we've got to expand that. And we have 1 over a plus c e to the minus kt as our general solution in terms of z. But remember, z is equal to 1 over p, so we can put in 1 over p equals this right here, and then invert both sides to get p as a function of t. And we have p of t is 1 over a plus c e to the minus kt. Now, we used a different approach to solve this earlier, so we have a slightly different form, but you can do a little bit of arithmetic or algebra to rearrange the expression to get it in the same way we got when we used the technique for separable equations. All right, that's all for today. Thanks.